So welcome back. So we are going to proceed with the second part of the mini course by Professor Tom Hurd. Tom, the floor is yours.
Okay, well, thank you for coming back. It's starting to get late on a Saturday. What's everybody doing Saturday night? As soon as I will stop, you guys can start to have fun. Okay, well, right, and a gross deficiency of the Eisenberg-Noe model is the zero bankruptcy costs, which means really contagion can't really take place. There's no kind of I don't feel that there's some active amplification happening. So Guy and Capati in 2010, they wrote down a much simpler model which assumes the worst, that during a crisis, when a bank defaults like Lehman, you're out for the whole amount. You can't recover any actual value any time that's useful to you. So you might have, Lehman Brothers, I think in the credit default swap auction that happened a week or two later, recovered. Does anybody remember what the recovery rate was on Lehman debt? No. I think it was like 7%. 7%, something like that. But then a couple of years later, this same debt was realizing close to 90%, I think. So it took a long time for Lehman debt to sort itself out. And meanwhile, the crisis was long over, it was well into the recovery. So Guy and Capati assumed 100% loss on defaulted debt. So the model is just exactly the same for us. Just put a tilde on the h function. And now h tilde looks like this. So as soon as delta goes negative, the creditors lose everything on that bank. Actually, there's a lot of reasons to like that model because it relates very strongly to the literature in random graph theory, and I may or may not talk about this more. Well, I'll talk about the Guy-Capati model more, but the relation with percolation theory, I think I will be talking about that. We'll see. I can't remember where it occurs in the slides. Okay, so Guy-Capati wrote a nice paper on the worst case assumption. Rogers and Verart in 2013, actually they introduced two parameters to two sources of bankruptcy costs. One was in relation to a loss on the endowment, and then kind of another fixed sort of fractional recovery value. So there were two parameters. It makes the model much more complicated for us because the recovery is not representable by a threshold function like this, because there's two variables that determine the fractional recovery rate, not one. So rather than use the Rogers-Verart or similar thing, I decided a very natural mathematical way is to interpolate between these two pictures. There's lots of ways to interpolate, but the one that I chose to look at is to introduce the threshold function h lambda of x, and it goes to the value minus lambda instead. So lambda is now between 0 and 1. So you see it's a steeper slope there, which means but it's also continuous. Okay, the Guy-Kapadia model is discontinuous. It actually creates some theoretical issues, this discontinuity, because the properties of the fixed point condition in the Guy-Kapadia model, nobody, as far as I know, nobody has any idea about the uniqueness of solutions. It seems that there's all sorts of possibility for non-uniqueness, and it's really kind of a mess. So, so this continuous threshold function is I think close to what you want for sort of a general workhouse kind of threshold function. So the advantage that it's only a function of one variable, so we can stick to a one buffer characterization of the state of every bank's balance sheet. So as you see from the fixed point, if you represent it as an Eisenberg-Noe equation, you see all that happens, essentially all that happens is the pi matrix gets multiplied by a number bigger than 1. That bigger than 1 is an amplification factor, and it destroys the resolvent expansion here. So it becomes an interesting the fixed point iteration will still converge because Tarski still works, but the relationship with the resolvent expansion is not clear to me. I haven't thought about it abstractly enough to say anything definitive, but I recommend it seems to be very interesting to look at, you know, from the point of view of the conditions on the fixed point. So in particular, it'd be nice to work out examples of non-uniqueness which are unlike the simple examples that occur here. Okay. So I call models with a threshold function that's continuous soft threshold model. It makes a binary model like this is combinatorially much easier to deal with than this kind of continuous threshold function. Okay, so that was the standard default cascade picture, and I've shown you how to vary it in different ways, but without really dramatically changing the complexity of the picture. So now I want to argue that there's a different kind of contagion connected with funding liquidity. And it too has an Eisenberg-Noe representation. So such problems have to do with debtors removing money from their deposit accounts. And so I'm going to just adjust the balance sheet to account for that. So a demand deposit requires that the bank so when there's some color here. Let's use a little bit of color. So when a big chunk of the debt suddenly is removed, then the bank basically has to pay that immediately. And so liquidity crises happen when banks become no ready access to cash. The channels to raise cash become blocked. So the general picture that we'll propose is that bank runs like this boil down to a problem of liquidity. And we're going to treat the cash reserves or the cash available, or if you like, highly liquid securities as being a buffer in the same way that delta, or the equity, was a buffer. Okay, so actually I'll introduce right away, I'll use a Greek letter, and I'll imagine situations where the cash position becomes negative. So there's various ways to think about that, but so the sigma is no longer always positive. When it is positive, the bank is liquid. When it's negative, we'll say it's stressed or illiquid. And let everything else be as before. Okay, so there's the picture. Okay, so the Guy Kapadia 2010 paper on default cascades had a actually I think it was 2011, had a sister paper called, well, there's the title. And it was designed to explain the shrinking of the interbank lending market during the crisis. And it happened seemingly without actual defaults. So there were defaults happening, but it didn't seem like these were part of the picture. The defaults weren't actually causing the illiquidity. And what was more likely explanation is simply that banks realized there was a liquidity crisis and they started hoarding liquid assets as a protection mechanism. And the first way that they tried to hoard is by calling or withdrawing their interbank assets from other banks. So you can see immediately, schematically, that if this bank decides to cut their interbank assets in half, essentially they're going upstream the arrow, back up the arrow, and coming and hitting the X position of a counterparty bank. So it starts to look like a mirror image of the default cascade. Okay? So yeah, so why don't you just do the mirror symmetry, flip assets and liabilities, map the cash buffer as if it was the equity buffer, and you see that our model, it's actually true. You can just take the model, the math model, and interpret it that way. So the Guy Kapadia model, well, the cash buffer after n steps is just the initial cash buffer minus the sum of shocks delivered by counterparty banks through the interbank exposures of 1 minus an h tilde function, the same h tilde function, in other words, a 0, 1 function, and the same fraction of the cash buffer divided by now the interbank asset rather than the interbank debt. So actually, it is formally identical to the Guy Kapadia default cascade. Okay? Now, I wasn't happy with that, so in my book, I just threw this down. It's never really been studied anywhere. I just still don't know if anybody's ever bothered to write it up and publish it as a paper. But a generalized liquidity cascade. You see what's happening in the Guy Kapadia model with the h tilde function being a 0, 1. This says as soon as the bank becomes illiquid, they recall 100% of their interbank debt. So in other words, they deliver the maximal shock to their counterparties. And so they're using the interbank assets as an extension of their cash buffers. So in the generalized liquidity cascade, banks keep cash, but instead of acting with 0, 1, all or nothing strategy when their cash buffer goes negative, they adopt an Eisenberg-Noe sliding incremental strategy of recalling only 1 minus this fraction, depending on the level of cash in relation to sigma divided by z. Okay. So instead of plugging delta over x, we plug in the cash buffer divided by z, and so that is, well, sorry, there's too many words here. I've just given you enough. That model I just described is precisely equivalent to the extended Eisenberg-Noe model. The extension meaning without this condition. Yeah. Basically, it doesn't seem natural in the liquidity cascade to have the original assumption of the Eisenberg-Noe model with y bigger than d. And so it comes out in the general case. And so it's worth thinking about the symmetry that relates the liquidity cascade to the Eisenberg-Noe default cascade. And of course, it amounts to mirror symmetry on the balance sheet, which is somehow seems intuitively obvious, but is not at all obvious when you think about it financially, that a cash or liquid assets would have or mathematical or formal similarity with equity. They're defined completely differently. It's not okay. So it is subtle, the nature of the symmetry. For the record, there's an earlier model by Lee, 2013. It's also an Eisenberg-Noe model, and it does it away with the cash altogether. It just assumes that every withdrawal of debt is paid for immediately through the interbank assets. So it's a degenerate case of an Eisenberg-Noe model. Okay. Okay. So the lesson there simply was that liquidity cascades, where the liability side of banks get hit by withdrawals from the external creditors, in other words, depositors or wholesale funders. Now, I'm working on repurchase agreements and repo financing at the moment, and the same thing holds. This Eisenberg-Noe picture is typically at the core of even quite general pictures of funding liquidity. Okay, so let me now go to yet another aspect of systemic risk, which also has a reminiscent Eisenberg-Noe kind of framework. So the liquidity spirals, the downward spiral in asset prices that you expect to see during a crisis, is not included in those two, in the default cascade, as I've described it. It's not included in the funding liquidity cascade picture, okay? So market liquidity has to do with whether marketable assets can be sold at or near their book price or pre-crisis price. So, of course, in reality, we expect that large categories of assets are going to be well, I think I wasn't here for Lakshi's talk, but I gather it was largely about market impact, so market illiquidity. So the market illiquidity models have to do with the valuation of external assets. And every loss in external assets value through a price change is reflected instantly in a loss in equity. Okay, so how do you include this? Well, this is called indirect contagion. So the contagion channels I identified have been bank-to-bank contagion. So within the financial system that's defined to be a network of banks. But every system in finance, there's an exterior that must be treated even if it's only treated in a very schematic way. So we have the exterior of the system not modeled so far. But indirect contagion are channels of contagion that go outside the system as it's defined, and then you then feed back into the systems. So in order to bring indirect contagion, which is what market illiquidity is, into the system, we have to bring parts of the external market and include it in the system. So then we add assets as red nodes in the system in addition to the blue nodes that are banks. And in the model of Cifuentes and Ferrucci and Shin in 2005, and Fabio Caccioli and Farmer and I can't remember the other co-authors in 2012, they picture what happens in a network of banks that have common portfolios or overlapping portfolios of assets, and then during the crisis, they do large-scale selling of these assets to realize cash to pay some of these problems of funding illiquidity. So very quickly, we might model it stylistically and say when a bank hits a regulatory barrier that triggers a shrinking of their balance sheets, they will shrink their balance sheets by selling what are illiquid assets that are held in the external system. And I'm not going to dwell on this model, but I just want to point out that every asset, the health of an asset during the crisis could be monitored by the fractional, the price of the mark-to-market value of the asset as a proportion of its pre-crisis value. So we saw that financial assets were down over 50% in value just prior to the Lehman Brothers collapse. And similarly, in an asset fire sale situation, the price P of asset A after n steps of the crisis acts just like a buffer or a health variable, and it naturally decreases monotonically during the crisis. So while banks' buffers are decreasing, the red nodes have the equivalent of buffers, which are their prices, and the impacted prices decline during the crisis. So now indirect contagion of price impact influencing banks with a common overlapping portfolio is now endogenized, is now within the system. And so that we're making indirect contagion kind of a direct contagion channel. Okay, so these simple models, if you see, I say these simple models, the blue nodes are governed by a default buffer variable. The red nodes are governed by their price, and it's analogous to a buffer variable. So these are simple. This is a simple extended picture where every node has one buffer. And so in these pictures, you don't care that much where the crisis starts, because in any developed crisis, if the initial trigger hits the banks or hits the assets, the end result is likely to be kind of the same. They're both going to bring the other down. Okay. So it doesn't really matter. You don't have to ask too much what trigger am I assuming. The modeling really covers all possible triggers. So now I want to go back to the asset liability symmetry. And it's sort of useful to look at the elementary balance sheet changes and ask for the mirror equivalence. And so, for example, when the price of an external asset drops, that you see the green impact, the value of external assets will be dropped, say by $1, and then that's 1-to-1 with a change in equity. The mirror image of that is a withdrawal of $1, which is 1-to-1 with a reduction in cash by $1. So this mirror symmetry is not quite that obvious. Why should the price impact on an asset be 1-to-1 with an actual change in the number of units of debt? So price on one side becomes the number of units on the other side. So it's not. Okay. Conversely, if that was number 2. An asset price decrease is delta y equals -1, corresponding to a delta E equity -1. That's dual to a deposit withdrawal. A mark-to-market drop in the value of the liability changes delta D by -1, but actually adds $1 to your equity. That's actually shifting the line, taking a piece out of there and adding it to your equity. That's dual to selling a unit of the asset and receiving cash, increasing the buffer of cash by 1. Okay? So the reason for looking at this symmetry is that it suggests a sort of natural way to combine multiple buffers. So if we want to now combine the funding liquidity channel with the default cascade, you sort of want to do you want a 2-buffer problem. You're going to have a cash buffer and a delta buffer, default buffer, and you want to interweave these two channels together to make more virulent contagion than you could get through any single channel model. And then in my paper, which was sort of a thought piece of last year, I put it all together, and this is kind of a schematic of the top 4 channels that have been discussed in the literature of systemic risk. Stand and look at it. First, be impressed by the symmetry of it. Okay? So it's actually it's not a reflection. What is it called? An inversion symmetric. Right? So if you rotate it by 180 degrees, it comes back and interchanges default buffers and cash buffers, interchanges assets and liabilities. Now, the dotted lines show the banking system on the inside, and the 2 bars on the outside are showing 2 aspects of the exterior market. On the left, we have the exterior debt pool, the pool of depositors and wholesale funders. And on the right wing, we have the assets, the external asset classes. And so the arrows that go from the middle to outside, the exterior, these are called indirect contagion channels because they go outside the banking system. But then they feed back in, right? So the S loop is resolving defaulted banks using the default contagion channel and depends on default buffers. The L cycle here resolves illiquid banks and involves their cash buffers and replenishing cash buffers. To replenish a cash buffer, you ultimately would have to liquidate some fairly illiquid assets, and that will create price impact. And then price impact impacts all the banks in the system because they have overlapping portfolios, and as we see, mark-to-market losses in assets are instantly reflected in a reduction in the equity buffer, which triggers subsequent defaults. At the same time, there's an idea that creditor confidence is kind of the dual of price impact. So as the external market is less confident of the price of assets, the price drops. As the external debt pool is less confident in the solvency of the financial system, they will withdraw from the financial system under crisis. So there will be withdrawals because of a drop in creditor confidence, which will then impact the cash buffers. So this is kind of my holistic picture of sort of what I think of as the minimal model of systemic risk. Should at least have all of these channels. Okay. Right. So, so it turns out the paper last year put together and it's essentially a double Eisenberg-Noe model, because literally I mapped the Eisenberg-Noe default channel and the Eisenberg-Noe generalized liquidity channel, and I threw them together and mixed them together. But in addition, I have asset fire sales and deposit withdrawals from the external, or this creditor confidence idea. So, so there's I don't think at this point I want to tell you about what happens. Let me just summarize it quickly. When you put the liquidity and the solvency together, the circle means you do one and then you follow it by, you do one single step of the solvency channel and then one single step of the liquidity channel. And then you iterate this. That's our single step of the cascade mapping. Of course, you might start with L and then follow that with S. That's sort of happening a half cycle later. So this is fully symmetric formally, mathematically, in the asset liability symmetry. If all the banks stay liquid, then it's the Eisenberg-Noe default model. If all the banks stay solvent, then it's the generalized liquidity model. You can write it in a reduced form cascade mapping, which is more complicated, requires more thinking than just a single. So there's actually fundamental issues with putting two channels together, because timing matters. Do you do this one and then that one, or do you do two cycles of the cash and then one cycle of the default, or what? So that's it. So all that makes a difference. There is a theorem. It's not immediately monotonic. you have to do some work. So it's not immediately an application of Ratarski fixed point theorem, but it is ultimately in that form. And in the end, there will be a maximal fixed point, sort of a best case outcome of the crisis, which would satisfy a fixed point condition. And in that fixed point, you can read off which banks have defaulted and which banks are illiquid. So the banks that are defaulted end up with 0 buffer, default buffer, and the banks that are illiquid end up with 0 for their cash buffers. Okay. Okay, so that's kind of my survey of just the general mechanisms that you would like to include in a network model. Now the question is, what does the network look like? Okay, so I'm just looking at the time, trying to think how we're doing. Okay, so this is where we change gears, and so I'm going to come back to the statement I made about self-organized criticality and say that in order to see the effective buildup of a system into a critical state, you need to have a very large system in order to see clearly that picture of self-organized criticality. So I've spent a lot of time working essentially in the infinite network limit and try to develop mathematics that crystallizes in some sense. So this is the literature that you're familiar with if you follow systemic risks. So Amini, Conte, and Minka wrote a really brilliant paper in like 2012 where they found the equivalent of an Eisenberg-Noe fixed point condition, but it describes the probability distribution of balance sheets in the end state of the crisis. So and it's a stochastic model with essentially infinite number of banks that so I'll be clear about that in a minute. So that's, I think, okay. So Guy Kapadia in the 2010 paper, they basically did a similar argument. It wasn't rigorously proved. So this is coming from the literature in random networks and percolation theory. Okay. So I'm telling you this story now because I want to motivate now changing the situation from just deterministic balance sheets to now imagining a system where, for fundamental reasons, we don't know what the balance sheets are. So, and that's true in reality. Brazil is notable for having perhaps being one country that the network is actually mapped out in a great amount of detail. And the paper that Rama Conte and Edson Santos and anyway, they gave a description of the Brazilian network with details, and that was a reflection of the fact that the central regulators in Brazil actually monitored all the counterparty exposures between banks, all different kinds, on a daily basis. So that kind of refined data is not typically available to anybody, in the EU, the EBA, European Banking Authority, has a subgroup of people, and they're trying to develop the databases for the EU zone, the Eurozone. As far as I know, it's still work in progress. The US, it's hopeless, okay? Bank of Canada has very coarse data on a monthly time scale about counterparty exposures in different asset classes. But fundamentally, it's very obscure what the network actually is at a moment in time. So given that it's not known, you have to have a stochastic model to model what it could be plausibly. Okay? So for that reason alone, it makes sense to talk about random financial networks. Another reason is if the connections are changing very quickly, which they do, they're jittering up and down, at an instant in time, the crisis may happen any time, and so the timing of the crisis may come at a moment when the system is already in a fluctuation of a certain kind. So for a lot of reasons, it makes sense to write down stochastic models. A third reason is that by using a stochastic model, you get to explore whether crises are generic or not. If they occur with probability 1 in this big random model, then it's kind of a robust phenomenon. Okay? All right, so random financial network is broken down here into 3 levels of structure. First, the skeleton just shows which of all pairs of banks actually have a significant exposure. So typically, you don't want an every bank to every bank network, because then network analysis is not very effective. And so typically, we have a cutoff and say only if the level of business exceeds a certain amount do we deem there to be a counterparty exposure between the 2 banks. Okay? So the network at a moment in time would have a skeleton, which is a random graph. And it could be directed random graph, or it could be an undirected random graph. Okay? So let's take it to be directed. So if it's an interbank exposure, we'll say it's directed from the debtor bank to the creditor bank. Of course, in time, that creditor relationship might be reversed. So for that reason, I'm not sure directed edges are really the best way to do general systemic risk. So for that reason, we might just identify undirected edges that represent a strong counterparty relation, which may go either direction. Okay, so here's a labeling for nodes in the network. If the edges are directed, then we need to count the in degree, the number of in counterparties, separate from the number of out counterparties. So it's a by degree for every bank. And we need to distinguish the kinds of exposures. So you might minimally think that exposures from an out 2 to an in 3 graph somehow behave differently from other possible edges. So you might want to label according to the number of counterparties. So this is a whole style of random graph model. I'm not stuck on that kind of model or that kind of labeling. Okay, so the second layer is conditioned on the counterparty relationships. Then you populate the nodes with random balance sheets. Well, they could be random. They might be deterministic, but okay, so whatever. You specify it as a second layer, random balance sheets. And then here, just to keep it clear, I'll call the third layer is an assignment of values of the exposures for every link in your random graph. And if you're really going to do fully developed systemic risk, all of these are likely to have subcategories and probably ultimately would be multidimensional variables. Okay, so in order to do theory results like the Amini-Cohn-Minka paper, also papers by Meyer, Brandes, Dettering, sorry, I'm just getting tired, Biagini, I guess. These are people who proved rigorous results for random networks in the asymptotic limit as the number of banks goes to infinity. So that's kind of the ultimate mathematical result that pleases people like me. So in order to do that, you need a specific kind of random graph. You need to be specific about the kinds of cascade behavior, what cascade mechanism, and in particular, you have to make really heavy-duty mathematical assumptions that actually remove a lot of financial interpretation from the result, in my opinion. So if you're really stuck on getting theory to work beautifully in n equals infinity, you're going to face a huge number of conditions that probably you don't really want to make. In particular, the choice of random graph model, well, the famous configuration models, Generalized the Erdős-Renyi random graph, which is the original random graph in the literature. So there's, this is not active. So that's one kind of model. And something nice has to happen with large n. And typically what has to happen for these results, well, let me not make I'm not going to make that statement. Okay. So aside from the Cohn-Amini-Minka model was some variation, a simplified configuration model. The Dettering, Thiele, Meyer, Brandes used called inhomogeneous random graph model, which is another generalization of the Erdős-Renyi random graph. But so this is the model that I actually prefer now. So my recent paper is on inhomogeneous random graphs. So if I was going to give a talk here during the conference, I would talk about this kind of random graph network, or the random network. Other famous random graphs are called the preferential attachment or scale-free models. So all of those are useful. Okay. So actually, I apologize. Stefano's here. This will overlap with what I told people in Le Mans a couple of years ago. So maybe since the day is getting late, maybe I'll end on percolation theory, but I could do a couple of mathematical calculations on the blackboard, which would be fun for me. And you might not find it that fun. So the reason these large N results work is because of some independent structure that becomes asymptotically true in random graphs where there's a bound on the total number of average number of counterparties. So as you scale the network up to 1 million, if you keep the average number of counterparties fixed and grow the network, then what happens is the likelihood of there being short cycles in the network gets smaller and smaller. So the density of short cycles goes down like 1 over n when you expand the network with a fixed degree or a fixed average degree. Okay? So you think about it, the cycles are what kill kind of a simple independence property that you might otherwise have. So in particular, if the network had no cycles at all and was just a tree, then, and you make bold assumptions that the balance sheets of different banks are drawn independently, then there would be no buildup of dependence structure. And that's kind of, in a nutshell, what's needed in order to prove these kinds of mathematical results. So you could, arguably, it's completely the wrong thing to do because networks are actually dense networks of counterparty relationships. I argue it's better than you'd think. Okay. So what I want to outline is basically just tell you that the hope is in these models is that you can get a picture of the cascade by looking at it as if it's actually on a tree, and if there's enough independence across the nodes, and if the mechanism that banks transmit shocks with is sufficiently simple. Then there's an underlying branching process, and that underlying branching process gives you kind of the essential understanding of what the cascade will do. Okay? So basically, I'll just end with a description of the Galt and Watson process, and I'll leave it to you to think how that might relate to a fixed point equation like this. Okay, so solutions of this equation where these are deterministic variables, that's the Eisenberg-Noe picture. What happens when we draw x, y, d, and the pi and the omega from random ensembles? What's the average recovery rate from a given bank? That's the kind of question that you end up addressing. So let's just do, because let me just see what else. Yeah, so there's a bunch of results here on percolations here. Let me just, before getting into the branching process, let me show you, this is just very, very simple realization of the Guy-Kapadia model, default model. The one with the 0-1 behavior. You see, all that matters in the Guy-Kapadia model is the bank alive or is it dead? And so, so this graph shows two things. The blue line is the analytical formula that you get from the large N asymptotics. And the red stuff is Monte Carlo simulation. It's completely trivial to simulate all of these cascade models in Monte Carlo for a finite number of banks. So, so I can't remember all the parameters of this thing, but the x-axis is the average connectivity, the average number of counterparties for the banks. And it's a very simple Erdős-Renyi random graph. And the balance sheets are pretty deterministic. They're pretty simple specification of the balance sheets. But the point is the analytical formula exactly matches the Monte Carlo. That's the first thing. And the second thing is that it shows dramatically different behavior depending on the parameters. And so the analytic curve is not quite, it shows a dramatic increase in the contagion just as the connectivity gets above 1. So it sort of follows that you have to have at least one counterparty in order to, on average, for contagion to propagate. Okay. But what's also kind of amusing is that it cuts off, the contagion cuts off if the connectivity gets too large. That's because the average exposure of a defaulted bank is divided by the number of counterparties, right? So the average exposure goes down as the connectivity goes up. And, okay, so if you're going to understand graphs like this, you have to understand percolation theory. If you want to understand the analytics, here's a graph. It's also showing analytical formula and Monte Carlo. Just the frequency that a given random trial exhibits a total number of defaulted banks bigger than 5% of the network. And there's a simple analytical formula, and it matches pretty well the red Monte Carlo. Okay? Right. Now, in my book, I analyze the Guy-Capadia model and give a much more general model in the Contamini-Minca version of the Guy-Capadia model. And my fixed point condition is much more complicated, but I can't prove a theorem like they can. I can only argue heuristically that this fixed point condition is correct. Okay, so that's just kind of motivation for you to take the calculation I'm about to do seriously. So just basically, I want everybody to know how to do this calculation because it's so nice. So think of this as the way a significant shock goes from counterparty to counterparty. So here we've got an initial default, and let's suppose it sends out a random number of significant shocks to its counterparties. Then we've got the nearest neighbors that get hit in the first round of the cascade. And then in the second round of the cascade, we may or may not, if this is a significant shock, maybe significant means it actually causes the neighboring bank to default, or something like that. It's pretty abstract. Just trust me that. So the idea is each generation, each node in the generation delivers some daughter at the next generation and of a certain number, and we'll say that the number of node I in the n minus first generation, this is the number of offspring, and we'll say they're all IIDX. They're independent and identical. Okay, so this is the simplest. So there's one offspring distribution from every node. And there's a sense of time evolving, so these are directed upwards. Okay. Right. So let's just, so the solution to the problem is what's the extinction probability? What's the likelihood that this contagion dies out in a finite number of steps compared to the pandemic outcome, which is that the size of the tree that's generated is infinite? Okay? So what's the probability? Okay, so let's let Zn equals the number in the nth generation. Okay, so Z's the number in the nth generation, and let's let the extinction probability be C. That's the probability that Zn is 0. Okay. Hands up if you've seen this problem. Okay, Max has done it, George has done it. Okay. Yeah?
Another incarnation.
Pardon?
In another incarnation.
In another incarnation. Yeah? Okay, cool. Okay. Right. So I wouldn't do it if it wasn't a nice argument. So what's the argument? Well, of course, there's an iterative structure here, which is absolutely essential. Zn is our sum with a random number of terms depending on the number in the n minus first dimension. You're just adding up all the x's for the nodes of the n minus first dimension, or generation. So this is sum, and this is xi from generation n minus 1. Now that's an independent sum, but with a random number of terms, right? So the solution that takes care of it is characteristic functions or generating functions or whatever. And that's why in my analysis I always use generating functions and characteristic functions. It's really the way to go in this kind of treatment. Okay, so the generating functions, if you like. Okay, so let's let g of s be the expectation of s to the x. So that's the probability generating function, I think people call it. And we only need s in the range 0 to 1. Of course, it's an analytic function of s. And let's let Hn be the generating function of Zn. Okay? Okay, so now we have a sum of independent variables, and so this is the product. I goes from 1 up to okay, so let's put, so what we're going to do is we're going to do this by intermediate conditioning. So we'll put it just condition on the random number of terms in the sum. Okay, so then on the inside, we know Zn minus 1, and so we've got a sum of a non-random number of terms, and so this is now product. I goes from 1 to Zn minus 1. And these, oh, sorry, these are not E's, these are zetas. I'm teaching, sorry, this is S. I'm teaching stochastic calculus, and we're doing moment generating functions all the time. Somehow the physicists like probability generating functions. Okay, so this is just a product of identical terms, and each term or each factor is just g of s. Okay. Now, what's going on? Yeah. But look, that's just the z n minus 1 power. So this is e gs to the z n minus 1. And of course, that is h n minus 1 of g of s. So now you see that hn is hn minus 1 composed with g. Of course, h1 is the same as g. So this is just g circle itself n times. So hn is simply the n-fold convolution of the fundamental g. And now we can do everything. We can see the final answer pretty nicely represented. Well, the extinction probability is just the probability that z equals 0. Well, you get that by plugging in what? S equals 0 into hn. So zeta n is just hn of 0. Yeah. Zeta 1 is g of 0. It's probability of getting no offspring in the first generation. And okay. So actually, I guess you can draw a picture here. 0, 1, 1. So g of 1 is 1. And g of 0 is bigger than 1, probably. And I guess all that really matters, g is also convex. So there's two possible pictures. So here's the diagonal. And you could do it this way, or it could do this. So there's two crossings or one crossing. So if you take g0 here, now if you take 0 here and then you go up to the curve, this is g0, and then you cobweb over and drop that down there, and then go up to the green curve, then you go like this. And you go to that fixed point. So the green one, the extinction probability is 1. So it means almost surely the cascade does not continue to infinity. And on the blue one, clearly it's starting below the blue circle, and clearly it ends up at the blue circle. Okay, so the end result is that the limit as n goes to infinity of zeta n is equal to zeta exists is less than or equal to 1. Moreover, zeta is equal to g of zeta. Moreover, zeta is the least fixed point. And zeta equals 1 if and only if g prime at 1 is bigger than or equal to 1 possibly there's a special case when g equals 1, I mean when x equals 1 deterministically. If there's one offspring every generation, then that's not in this set. And say g of x is not equal to x. Yeah. So if the slope, sorry, I got the wrong way around. Less than or equal to 1. Yeah. You got to exclude the case that x is deterministically 1. But otherwise, that's the case. Okay. So it's easy to show that it's a fixed point. It's easy to show it's the least fixed point. And it's easy to show that the condition for there to be two fixed points, in other words, one fixed point that's less than 1, is that the derivative at 1 should be bigger than or equal to, bigger than 1. Okay? Right. So this is the kind of probabilistic fixed point theorem because it's the extinction probability that satisfies this fixed point condition. So in the Guy-Kapadia model, if you do it in the Amini-Conch-Minka theorem, it says that somehow a conditional probability that a given node ends up defaulted, call that probability pi. There's an explicit function, pi equals g of pi. And there's a non-trivial fixed point, non-zero fixed point, if and only if the derivative of g is essentially bigger than 1 or not. Okay? So that's the nature of these infinite percolation results. And I would say they form kind of a mathematical center for the theory of systemic risk that we'd like to see happen in much more complicated models. So rather than show you all the remaining slides, I think I'll end on that note and encourage you all to go out and have fun tonight. I might go home to bed.
Okay. Well, thank you. Thank you so much.
Thanks for